Okay.
All right, next slide, please.
Mhm.
So we're gonna give an update on autonomous machine computing. It's been a very popular topic in the past year. So in IRDS 2022, we have given an overview of the technology around autonomous machine computing. And in today's talk, IRDS 2023, we would like to provide some updates, particularly in two areas. First one is the computer architecture evolution for autonomous machine computing. The second topic is reliability. Can we move to the next slide, please? So in the past decade or so, when we talk about autonomous machine computing, whether the machine being a robot or autonomous vehicle, it has a pipeline like this. It's a quite modular pipeline, such that you start on the left end with sensing, then the sensing data goes into a perception module, localization module, then it advances to next tracking, prediction, planning, control. So it has been a modular design. And from the computer architecture community, people have designed many different accelerators for each module. The original target was to integrate all these accelerators together into a system on chip, such that you can map different workloads onto a system on chip, and then different accelerator models would be able to run in parallel to accelerate the whole workload. Next slide, please. But this has changed since the emergence of the transformer architecture, especially popularized by large language models such as ChatGPT, Hugging Face, and so on and so forth. The recent advancement is that you will be able to use, for example, one vision transformer to take care of all the perception localization tasks as one module. And then people are designing a language model to perform the backend tasks such as planning and control. So that kind of simplify our module design such that you have two transformer architecture such that on the left side, if you look at Autonomy 2.0 figure at the bottom, you have one transformer to take care of all the vision tasks. Such a transformer is able to fuse different sensor inputs such as GPS, camera, IMU, LiDAR, whatever sensor you have today. It's going to jam into this one transformer. And then this transformer is going to produce what we call a BEV, bird's eye view representation of the environment. And this can be universal to all different kinds of robots, such as vehicle, mobile robot, home service robot, cleaning robot, and so on. They can use the same representation, and then the whole representation can be passed to the backend, which is the action transformer. So we are seeing a trend with a two transformer architecture being able to handle most of the autonomous machine workload. So instead of the module design, you see a autonomy 1.0. We now see a newer architecture with two modules. So the key questions for IRDS community is how do we accelerate this kind of transformer architecture to produce the best output, the best performance. A third question would be, would that mean one accelerator is enough for autonomous machine workload? For more details, I'm happy to refer you to this paper, Autonomy 2.0. We explain the logic why the whole industry is transforming to this kind of architecture, especially with the recent release of Tesla's Dojo design. It's pretty much emulate after this design paradigm, which is a two transformer architecture. Next slide, please. So not only that, our architecture has changed, such that maybe in the future it will be simpler to design computing systems for autonomous machines, such that you have a, for example, control CPU, then you have one or two accelerators for transformers. That may be sufficient already. But then again, the whole industry is still blocked on data. Even if you have a very nice transformer, how do you generate enough data to feed into a transformer so they can learn how to navigate through the environment? And that's the second piece of work we have done. It's called design automation for autonomous machines, such that you can generate a simulator, a high-level digital twin, to generate a vast amount of data. The data will then be fed into the first transformer, which is the vision transformer, to compute the environment variables. Then with that, you pass the whole BEV to the second transformer, to do planning and control, then you finish the loop. So that in our vision, there are only three components in the future autonomous machine designs. You have a front end transformer to do all the sensor fusion tasks to give you a full perception of the environment. Then you have a back end transformer to perform your action for the robot planning and control. Then sitting in the middle is the digital twin to generate data to train these two transformers. So that's the vision of our current design. Next page, please. But there is a problem when we talk about autonomous machine systems. Reliability is the number one goal because that's directly related to safety. If we look at examining any existing systems, such as the drones you see here, the cars, the mobile robots you see here, there are many places you can inject faults, or the sensor itself may fail, whether at the sensor side or at the compute side, whether it's CPU, GPU, or accelerator. There are many traditional techniques, redundancy being one. You can have the same circuit run twice, or you can duplicate the circuit 2 or 3 times to make sure that the whole system is stable. But if you use a brute force technique like that, it will be extremely expensive to develop a system like that. So we've been exploring techniques to guarantee system reliability while not increasing the cost too much. Next slide, please.
You have 4 minutes.
Of course. So this is the piece of work we've done. We have a keen observation that when you are looking at a front-end task, such as perception, the software itself, being a transformer network, is quite resilient to different kind of thoughts, such that if you can use a software-based protection technique, it's sufficient to make sure that the front-end system is reliable enough. Whereas the back end, the planning control, if you have any kind of fault happening, a software technique is not enough. So you need a hardware technique to protect the back end. So that's a very simple conclusion that for future design, when we talk about the front end perception side of autonomous machines, you can apply different kind of software-based protection techniques. Whereas for the back end, you really need to do fault tolerance in the hardware, such that you duplicate the number of circuits to make sure that the computation is correct. So that's our high-level conclusion. Next slide, please. So pretty much these are the two quick update for IRDS 2023 autonomous machine computing, such that the first update is that we have a new architecture because of the software change. Now the hardware design may change as well towards a much simpler design. You have 2 modules and 1 digital twin in between. Second of all, with this change, when we examine the reliability of an autonomous machine, we realize that in the front end, the network itself is quite robust, such that you only have to apply software protection technique at the front end. But in the back end, it's very mission critical. As a result, you have to apply hardware techniques. And on top of that, I do have one ask to the community. We've been, for autonomous machine computing, we've been focusing on the system side and the software design, architecture design, but we have not delved into the technology side. Hopefully with the IRDS community, if you are interested in autonomous machine computing, you can talk about, for example, how 3D stacking can help in this particular application, how different kind of technology, such as nanosheet, for example, can help autonomous machine computing. With that, I would like to conclude my update, and thank you so much.